So, good evening, everyone. Welcome to the very first live interaction session for the polymer concepts, uses, and sustainability course. So, let's just wait for a few minutes before we begin our session for today. So, since it's our very first live interaction session, I think it would be better if we can introduce ourselves. So, myself, Pratyumnan. I am a PMRF scholar in the Department of Chemical Engineering at IIT Guwahati. I will be conducting the live interaction session for this course for this particular semester, that is July to November semester. So, likewise, it would be better if you all can either unmute yourself and introduce, or if you're not comfortable, then you can also use the chat box to introduce yourself. Yes. Yeah, hello. Yeah, that's fine. So, Nandini, from which background do you come from? Like, are you a... Okay, 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 fine. Yeah, that's nice. Yeah, that's... yeah, sure. So, we will try to... I mean, if you have any doubts, you are always welcome to unmute yourself and then ask at any point in the entire 2 hour live interaction session. So again, you guys can also type in the chat box if you feel uncomfortable, or if you are in a place where you cannot unmute yourself, then please introduce yourself in a chat box, your name and what you are currently doing, and what do you expect from this course. We will start within a few minutes. So this is a live interaction session, so it would be like the purpose would be served if everybody starts interacting. So I urge everyone to uh, what do you say? I urge everyone, like, if you have any doubts when I am going through the slides, then please let me know, or if you're stuck at any point, then I will try my best to solve the problem at that moment. So Monisha is saying hello Monisha. So you're doing chemical engineering at SSN College of Engineering. So that's nice. Okay, Abhinav is saying he's also pursuing chemical engineering at Savida Engineering College. Divyashri, she is also in the second semester of chemical engineering at BMS. Nice. Yatin is saying he's also pursuing chemical engineering from Savida. Okay, that's nice. So I think we can start our first live interaction session. So the very first live interaction session for this course will be more of the introductory part, where we will be discussing what is polymers. So starting from the fundamentals of, oh, Kalishwari Armugam is from rubber and plastics technology. So it will be, this course exactly matches with their curriculum, I believe. So yeah, let me share my screen. So let me introduce myself once again. So welcome everyone to the very first live interaction session for the course Polymers, Concept, Property, Uses and Sustainability. This course is offered by Professor Abhijit P. Deshpande from the Department of Chemical Engineering, IIT Madras, under the NPTEL SWAYAM program. So myself, I am the teaching assistant. I will be conducting the live interaction session. My name is Pratyumnan. I am a PMRF scholar, a PhD student at the Department of Chemical Engineering, IIT Guwahati, Assam. So, going on to our concept, or for the course content, the very first thing of the course is what are polymers? So, polymer specifically, it's more of an engineering term. In common, or for a layman, a polymer is nothing but it is a plastic. So every day we deal ourselves with plastic. We live with plastics, to be more honest. So starting from the morning to the night, we to the night time we go to bed, we always use plastics or polymers for our everyday needs. So, can you say some examples of where do we use polymers? As I said, from the morning, the very first thing what we do after waking up till the night bedtime when we go to sleep, we always deal with polymers or plastics. So, can people tell examples of what kind of plastic products you use in your daily basis? Yeah, we deal with plastics every day. So, some examples of plastics or of polymers. Very common examples of plastic. I mean, I am very sure that all of you will be knowing what kind of plastics we use. And since we have many engineers in the live interaction session today, so they even might be knowing what kind of plastics it would be, like the exact chemical name for those plastics. Am I audible? Oh, we have many. Okay, we have many answers. So polyethylene bags, PVC pipe, bottles, spectacles, toothbrush. That is exactly the very first thing that we do in the morning after waking up is to brush our teeth. So the toothbrush, the bristles in the toothbrush is made up of polymers. Then the water bottles that we drink, at least majority of us, if not all, we use PET bottles, polyethylene terephthalate bottles for our for for carrying water. And the electric switches are made up of plastics. And the for majority of for some of us, the containers in which we pack our food is made up of plastics or polymers and whatnot. So that's the reason I said polymers are there all around us. They are with us. They are blunt in our lives, and well, they may have, I mean, environmental concerns, and there might be initiatives wherein they would like to completely mitigate or completely eliminate plastics. But again, since it has been there with us for quite a long time, uh, we can try to reduce the usage of plastics, but completely eliminating plastics will be a more difficult and tricky um, idea. So, as such, what I let's so coming to this concept, coming to this course, so this is more of a fundamental course wherein, or you can say a introductory course wherein we will see what are polymers, how they are processed, and how they are, and what are their properties, what are they use, and we will also discuss about the sustainability. So that's how it goes. Concept. So we will learn what are polymers, how to process those polymers, the different types of structures of the polymers, and then we will deal with their properties. So what are the different kind of properties that polymers exhibit, and then where are these polymers used, or where are these polymers used, both from this common day to day applications to the engineering applications or the scientific application. And then we will also discuss about the sustainability part of polymers. So what's a polymer? So polymer, as I hope everybody will be having an idea, but let me again reiterate it. Polymer is a chain of monomers which are connected in series together. So a large number of repeating units together, when they are connected together, what they form is a polymer. So if you see here, you will have a lot, it's a polymer is a very big chain. The monomers connect themselves in very large numbers to form a polymer. So if you see here we have a polymer chain, and the n over here represents for the number of repeating units, and each unit over here basically represents for the monomer. So monomer as such, it means that single unit. So mer is means unit, and mono is single. So if two monomers combine, they form dimer. A dimer and a monomer, if they combine, they form a trimer, like the tetramer, pentamer, hexamer. And if it keeps on going after a particular uh, after a particular shorter amount of chain, the structure that we get, we call this as oligomers. Beyond that, if these oligomers keep on connecting with each other, what we form is a polymer. So the question comes to our mind is, as I said, the polymers are very common. They are there. We use them every day. So why is that so? So if you see as an engineer in the classes of material, we have metal, ceramics, and plastic. So these are the three main classifications. So in among these three classification, why is this polymer is more attractive, or why is this polymer um, is used more commonly compared to the other two? So if you, I hope everybody would have also went through the course. So in that course also, Professor Abhijit Deshpande sir would have told that polymers were discovered only 100 or 150 years ago. It's not like the other two classes of material that existed quite long back before even the invention of polymers. But still, or you can say, yeah, before the polymers even came to discussion. So but still, even within this very short span of time, or within this amount of time, the polymers have become more widely used. They are commonly used by us. So what is that, uh, what makes polymers attractive? So there are multiple advantages. So one is that it is basically, the very first thing to say is wide range of properties. So polymers can exhibit multiple properties, like range of properties. So it can be hard, as well as it can be rigid, as well as flexible. So if you see your PVC pipes, so they are very rigid in nature. However, if you see rubber bands, they are also made of polymers, but then you can actually stretch them. They are very flexible. Then the second part is the fabrication process. So polymers can be melted, and then they can be compressed into multiple other shapes using different processing techniques. So polymer processing itself is a one branch of study. So if people are interested, then there is a separate area for this called polymer processing. So there we have many methods to process polymers, starting from extrusion. Then there is something called fiber spinning, injection molding, um, and so many different varieties of processing the polymers to form different shapes, complex shapes, so that it can be used for daily applications. And then the third point is it's cheap. So unlike the metals or ceramics, the polymers are cheap. They actually have a low cost raw material. So as far as this advantage is concerned, the are attractive, but at the same time, these advantages can also be a certain disadvantage for the polymers. So since these polymers have a wide range of properties, which basically is due to their macromolecular nature, such a big polymer chain. So because of this macromolecular nature, they exhibit variable properties. So since it exhibits variable properties and it depends upon the macromolecular nature, each and every aspect of the polymers will change depending upon the molecular weight of polymer. So three things will be a governing factors which will guide the polymer properties. So first thing is your molecular weight, then it is your first is the molecular structure, next comes is the molecular weight, afterwards it is the distribution of the molecular weight. So how narrow or broad is the molecular weight distribution? So that kind of gives an idea about how long or shorter the chain is present in a bulk sample. So that basically governs this properties, and that is the reason we have a range of properties. So since there are lots of since there is a variable property, we need to keep in mind all of them while taking a particular decision of whether a particular polymer can be used for a particular application. Then comes physical aging, then comes durability, whether the polymer product that you are going to use, whether will they be durable during their service life. So service life is the life in which you use that polymer product. So whether they will be durable within that period of time or within that service life. So that is also is one of the factors that affects the polymers, or kind of can be considered as a disadvantage for polymer. The fourth point is the sustainability. So we told that the polymers are cheap because they are basically obtained from the low cost raw material. So these polymers are typically obtained as a byproduct from this petroleum resources. So since these petroleum resources are non-renewable in nature, so this basically creates a problem for the polymer. So they are coming from a non-renewable resource. So that questions the polymer sustainability. So that is from the raw material perspective. Apart from that, this polymers, since some majority of the polymers tend to degrade or take a long time to degrade, so that its use as well as the waste management of the polymer also creates this sustainability problem. But even though it has limitations, but polymers are becoming more and more attractive, not just from the day-to-day life but from the engineering perspective. So can anyone tell me what kind of scientific applications these polymers are used nowadays, or as far as you guys know, where are these polymers used in scientific fields or in scientific applications? Oh, am I not audible? Can anyone confirm whether okay, so the question is, so polymers have both advantage or as well as disadvantages. So but still polymers are being used, and they are more attractive to for research purpose. So they polymers are being used for many scientific application process. So can you please tell me, or as far as you guys are aware, any scientific application where these polymers are used? Uh, Semiconductor processing, yes, that is one place where these polymers are used. Apart from that, and I hope I'm audible now, basically without uh, uh, Arumugam, I am not able to get what you're actually wanting to convey to me. So could you please, I mean, if you can unmute yourself and then speak out, it would be good, at least in biolabs. Oh yeah, see, gloves, switches, all those things are common. They're used in daily life to life, in daily life. So I'm talking about the scientific applications of polymers. Somewhere in your biolabs, have you used these polymers for some aerospace? Yes. So yeah, I was saying. So have you, or have you like experience where people use polymers even in this biomedical application? Solar cells, yes, polymer solar cells are becoming are they are becoming of a great interest to use in solar cells, specifically making all the components of the solar cells completely go polymer based. Not just that, as professor also said in this course, it's not just about making the top cover of the solar cells with the plastic, but then every single component within the solar cells go plastic. That is a very great achievement of using polymers in solar cells entirely. Automotives, yes. And apart from that, polymers are typically used even in energy storage applications like batteries or other energy harvesting devices or storage devices like supercapacitors, fuel cell, soft robotics, sensor fields, plastic electronics. So the flexible what do you say, flexible phones, or if you can basically, so the major reason why they are becoming attractive is basically because of their flexibility, specifically in the sensor field. So in the electronics field, to be of to speak about. So yeah, soft robotics, plastic electronics, plastic transistors, and sensors, wearable sensors. So yeah, construction purpose also polymers can be used. That's right. So many different applications. Yes. Yeah, go ahead. You can call me sir. So there, typically when you do this petrochemical processing, the byproducts that are generated is used for this polymer production. So again, you need to actually go into the specifics of this process. So that is the reason I'm not going to cover on that. Yeah. Fine. Okay, so let's move on. So this is about plastics and how polymers are typically used. So multiple different monomers are present which can be reacted with each other or combined with each other to form polymers. So we will go through few of those examples, but not as in the form of a discussion, but as in the form of a question. So we will be having a set of questions, around 7 or 8 of the questions towards as we progress through the lecture. So let's just, so since this is our first live interaction session, I would like to tell that we will dedicate about 30 to 40 percentage of our time towards discussing or as a recap of what was actually discussed in the course. So we will just go through some of the important things that was already discussed by the professor as a recap. Then the rest amount of the time we will devote to Q&A, like what do you say, solving problems. So we will have multiple choice questions, numericals to actually go through, so that it's something very typical of what assignment problems that you will solve. So yeah, so there are multiple, coming back to the course, so there are multiple monomers which can react with each other under different reaction conditions to form a polymer. So yeah, so here, like I'm just skipping certain section of the course and then moving to tacticity in polymers. So polymers as such, their properties are, if you see this process of doing the polymer processing and their structure and then the properties, all these three concepts are interrelated to each other. They're interrelated and interdependent on each other. So depending upon the type of properties that you want, if you vary this process as well as that of the structure, you can get your properties. And sometimes based on the structure, you can vary the process. And sometimes you can, what do you say, for a particular process, you will get a particular structure and property. So all these things are very interrelated to each other and interdependent on each other. So in this so that's how it goes. So the structure of a polymer basically affects the property of the polymer. So we need to control these molecular structures so that we can get the desired property of the polymers, which can be used in specific applications of our interest. So in order to control the molecular structure of polymers, we need to talk about a concept called tacticity. So tacticity is nothing but it basically gives us an understanding on the arrangement of the uh, side groups in the hydrocarbon chain or in the polymer chain. So based on this tacticity, it's a kind of an arrangement of this groups in a polymer chain. So based on this tacticity, you might wonder. So yeah, let me talk about the tacticity first. So based on this tacticity, the molecular structure will be different, and this will change the properties of the polymer. So tacticity is not a very trivial thing. It's a very important aspects in polymers. So if you see here, so tacticity as such is of three different types. One is syndiotic, another one is isotactic, and another one is atactic. So in case of isotactic, what happens is the side groups, or if you see in case of this polystyrene molecules, all these benzene ring are arranged in the same direction or is on the same side. So when these side groups or when the groups within the polymers are arranged in a particular, then those kind of polymers are called as isotactic polymers. If these benzene groups, whatever you see in case of polystyrene, if this benzene group is on either side of this hydrocarbon chain or if of this hydrocarbon chain, then those kind of polymers are called as syndiotic polymers. If these benzene rings are randomly arranged, if you see in case of the molecular structure which is present in the middle, if these benzene groups are randomly arranged, then this can be called as atactic. So if they are all on, if all of them are on the same side of the polymer chain, it is called isotactic. If they are in a if they are alternatingly on either side, then you can call this as syndiotic. If they are randomly on arranged, or if they are on either side in a very random fashion, then you can call this as a tactic. So based on this arrangement, the properties of the polymers will change. So that's the reason I said tacticity in polymers is not trivial, because the arrangement of these groups within the polymer chain will have a huge influence over the properties of the polymer. So this is one of these ways in which you can control the properties of the polymer. Apart from that, we have to discuss about, so in order to do this, we need to actually look at how we polymerize the monomer. So depending upon that, this can be changed, and depending upon this tacticity, your properties can be changed. So coming to polymerization, there are multiple different polymerization techniques. You have, uh, I hope everybody will be know, since people have been through the course, you guys will be knowing better. So can anyone tell me what kind of polymerization or what are the different type of polymerization reactions you guys are aware of? Yeah, I think polymers is something people are learning since I think higher secondary. So even there also we are basically introduced to this polymer concepts, and few examples are also people might have learned. So can anyone tell me step? Yes. Step polymerization, olefins, yes. Free radical, step growth, yes. And another one is this, yeah, step polymerization. Again, we have this condensation polymerization, which is also one of the steps. uh, yeah, graph polymerization, yes, that's very good example. So yes. So can anyone tell me what happens in this case of step polymerization or free radical polymerization? How does this polymerization happens? Okay, then other kind, free radical polymerization. Again, free radical polymerization is also some sort of an addition polymerization, wherein the free radicals will react with each other to form monomer, and then so ionic polymerization, yes, ions will interact with each other, free radical active centers, yes, so that is fine. So based on this free radical polymerization, we also have something called catalyst based polymerization or catalytic polymerization. So wherein we try to add catalyst to, as somebody rightly said, to generate active centers. So one is basically the Ziegler-Natta is used as the catalyst, and another one is the metallocene, which is used as a catalyst for this polymerization. So again, each one has its own advantage. So if you use in case of this metallocene polymerization, then you will be able to get polymers with a narrow molecular size distribution. So a narrow molecular size distribution polymers will be useful for its further processing, because all the chains of the polymers that is going to be there within the sample or within the bulk that you're taking under consideration, all will be of similar length. So the processing of this polymer is going to be easy. Then we come to the last aspect of our discussion, or we do have a discussion on molecular weight and its distribution, but that will be discussed as questions. So talking about the sustainable use of polymers, so one is its raw material, and another one is its waste management. So we use polymers after the polymer gets used up, we just it gets thrown in the form of oh, oh yeah, there was a internet connectivity issue. Oh Let me share my screen once again. So yeah, we were discussing about the sustainable use of polymers. So first thing is its raw material. That is the issue because it is obtained from this petroleum products. Second thing is the wastage that is generated out of these polymer products. So how to deal with this wastage, or can we do this polymer recycling, or even if we recycle after, for how many times can we recycle these polymers, and many other different challenges are there with this polymer sustainability aspect of this polymer products, because the degradation of the polymers usually happens, but it takes time. It does happen through a lot of variety of processes. I hope majority of you might be aware, like some using temperature you can degrade the polymers, using oxidation, catalyst, or hydrolysis, radiolysis. So there are multiple ways to degrade this polymer, but the question is about how long it will take for the polymers to degrade, and what about the waste management aspect. So this is basically a more of a important research questions within this field about how to manage waste, because if you see, we do hear about the term of microplastics everywhere in today's world. People have also identified microplastic in several organs of the human body, so which means that people are containing microplastics or plastics which are in the micro scale within their body. So this is evolving to be a global challenge. There are many works that is going in and around the world about how to detect these microplastics, or because since they are in the micro scale they are not visible to naked eye. So how to detect these microplastics that is present in the water, or any uh, other forms in which they are contaminating it, how to detect them, how to manage them. So all these come under this sustainable use of the polymer and leave us with many questions which are yet to be addressed and solved. So we haven't discussed one thing, as I said, which is nothing but the molecular weight distribution. So that we will do as we progress. So let's, as we said, now we will be moving on towards this problem solving session or practice problem solving session, wherein we have a set of few questions. I have taken these questions, and then I will be reading it loud. So I expect answers from you. So before moving on, do you guys have any questions in what has been discussed till now, or within the course on this discussion aspects of that course, concept wise? Yes, yes, yes. Please go ahead. So actually, this metallocene is nothing but it's actually a complex compound. So what happens is that this metallocene has a metal atom at the center, and then it is connected on either side of this metal. What you have is a ligand, and these ligands are aromatic ligands. So this is a particular complex, and this is called metallocene. This basically acts as a catalyst in the polymer synthesis process. It basically generates I'm exactly not sure about that, but this is basically used as a catalyst, and this will be generating the free radicals for this polymerization reaction. But if you want to know more, then you need to read more about the polymer chemistry aspects of this synthesis, because it is indeed it's a separate what do you say, uh, a separate world, a synthesis of polymers. What are the different ways you can do this polymer synthesis? Because what we are discussing so far, this Ziegler-Natta catalyst of free radical polymerization, condensation polymerization, all these are discovered long time back. These are the other processes which have been developed in the recent days and they're coming up. So again, so this will be entirely a different what do you say, area in polymers. So we need to see, look up in the net or in the internet to learn more about this polymerization based on this metallocene. So I would suggest you, uh, to look up in the internet to learn more about this metallocene polymerization. So olefins, you asked what kind of bonds are formed in this olefins, right? It would be a double bond. Hello. Oh, it would be a double bond, because olefins is a typically a term which is given for alkenes. So it should be a double bond. Okay, yeah. Yeah. Yeah, go ahead, go ahead. Hmm. Yes. Hello. Oh. Hello. Oh. Uh, could you please repeat? Actually, there was an internet connectivity issue. I didn't hear you actually. Yeah, yeah, you are audible. Okay. Yeah, it's okay. So we have few set of questions, and I hope I'll be able to address all your queries there. So just wait for a few minutes, like around 15 to 20 minutes, we'll be reaching that section. So I hope when we will be solving the problems, you will get more understanding to that. Will it be fine? Oh, okay. Yeah, 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 fine. So, we will start with a very simple question. I hope participation from others as well. So, here it's a very, very simple question. So, match the following polymer in column 1 with their respective monomer in column 2. You can list me what could be, you can list out like 1, 2, 3. and 4. Q3. Okay. Yes, Q is 3. Polyvinyl chloride will have a chlorine atom attached to that vinylic bond. It's a vinyl ring, so 3. And then 1s. Okay, 1 is S. Okay, yeah, that is a very simple question. So polyethylene is 1s, then 2 2p. Yes, 2p, so propylene. So the difference between ethylene, polyethylene and polypropylene is basically that the methyl group which is attached to this carbon atom. In case of polyethylene, it will be a high. It will this particular bond will have a hydrogen atom. Here it's a methyl group, and so again, why is the 3 is written as Q? Sorry, and the last one, fourth, polystyrene will be R, because 1s, 2p, 3q, and 4 4 is R. That is polystyrene. So here it is basically the, if you see, it is just that one particular the only one, this hydrogen atom is substituted with the other functional groups, or to be saying with the other groups such as chloride, methyl, or it is the benzyl group. And this substitution with the different groups basically give it different properties. So if you see polyethylene bags and if you see polyvinyl chloride, so those two are completely different. Again, polyethylene, I mean this the one that you use in the PE bags. So this substitution of this different atoms in this monomeric unit basically gives a completely different properties to the polymers. So I hope this might be a very easy one. Nobody might have any doubts. So let's move on to a similar question. State the monomers for both nylon 6 and nylon 6,6. Yes. Okay. So for nylon 6, it is caprolactam, and nylon 6,6, it is hexamethylene diamine and adipic acid. So let me just show this how the reaction will occur, because depending upon that I have few other questions that I would like to ask. So I hope everybody would be able to see. So we have an epsilon caprolactam that when you heat it between 533 Kelvin to 433 Kelvin, you will get a linear chain, and this linear chain will basically react further. I mean, in the presence of catalyst, it will for the active sites will be generated, and then they will what do you say? They will undergo further reaction with the other monomers to form the polymers. So what kind of reaction is this? Leave about nylon 6,6. So nylon 6, it is, you say nylon 6 is a condensation polymerization reaction. So it is something called as ring opening polymerization. So here it's a cyclic molecule, right? So it's a ring. So this ring, in the presence of, or when subjected to temperatures of 533 to 543 Kelvin, that is somewhere around 250, mm, uh, 260, yeah. So 260 degrees Celsius, when you subject this epsilon caprolactam, then what happens is the ring of this ring will break, and because of this breakage the free radicals will be there, and then they will react with each other to form this nylon 6. In case of this nylon 6,6, it is simple condensation polymerization, as somebody just told to me right now. So here what actually happens is this OH group in this adipic acid will react with the hydrogen atom from this NH2 or amine bond in hexamethylene diamine, and then they undergo condensation reaction by eliminating water as a product to form this nylon 6,6. So what is actually, so again I have two more questions. What are the uses of nylon 6? Nylon 6,6 uses are, I can get, it can be, it is used in ropes and in other daily applications. But what about nylon 6? Any idea on where this nylon 6 is used? Okay, okay, yeah. So those are correct. So they are basically used in textiles, and then they are used in automotive parts. So this nylon 6 basically have excellent mechanical strength. So because of this excellent mechanical strength this nylon 6 possesses, it can be used in engines of automotives, and then it is used in fuel tanks. And apart from this automotives, this nylon 6 is also used in biomedical industries, specifically for making the surgical sutures, catheters, as well as in case of this biomedical textiles also this nylon 6 is used. So that makes nylon 6 a very attractive polymer. So my last question is based on nylon 6,6. What kind of polymer this nylon 6,6? Is it a polyester like your terephthalic, I mean PET bottles? PET bottles, I hope everybody will be knowing. It is the terephthalic acid and then the ethylene glycol together to react, and then they form, the water will get eliminated and they form a polyester. So similarly, what kind of polymer is this? Yeah. So it's a polyamide. And why it is a polyamide? Like any specific reason to call this as an amide? It's a polyamide, but any specific reason? So amide group is this C double bond O NH. Is it because of that? Bond. So, okay. And final, it's a very simple question, but I prefer asking all the time. Why it is called as nylon 66? Why? What does that six actually represents for? In their structures? Yes, that's absolutely correct. So let's go on to this. And it is one more thing I want to note down here is it's epsilon caprolactam. It's basically because of the way this carbon atoms are numbered from alpha, beta, gamma, delta, to which this NH group is attached, and that is the reason we call it as a epsilon caprolactam. So, yeah, I forgot to mention. So this question was actually taken from GATE 2021. So for your information that this question appeared in GATE 2021 in the engineering science paper. So yeah, so if you want you may go and look at that later. So let's move on. The next question is which of the following is an example of a biodegradable polymer? I hope nobody has any questions related to that. Yeah, polylactic acid, PLA, everyone is fine. So, any specific reason for why this polylactic acid is biodegradable, but others are non-biodegradable? Okay. Any other reason? So, yeah, you may look at the reason of why. Okay, that's correct. But again, I would actually want you to look from the what do you say from the chemistry aspect also a little bit more, go more in detail towards the structure, and then let us discuss this in the next class. Is there any other reason of why certain polymers can degrade in the environment whereas the others cannot be degraded? And also this I can put it as an open question to all of you here. Can a synthetic polymer be made biodegradable? Can we make it biodegradable? So we have some synthetic polymer, or can we do some changes to the synthetic polymers in such a way that it can degrade? So you guys can always look at some information within the internet, and then if you get anything interesting, then you are always welcome to share in our live interaction session. So yeah, this I'll be just keeping it. So again, why? So since nylon is a polyamide, so this polyamide 66, if you see, is similar to, is nothing but it is nylon 66. So since nylon is a polyamide, so they have, so it can be interchangeably used. Again, this is also one of your gate questions from gate 2023. Again, engineering science section. So let's move on. First, let's do the question number 7 and then move to question number 6 and then let us move to question number 5. I want the question number 6 to be done first before we move to question number 5. Determine the functionality of adipic acid. I hope you know, everybody knows what an adipic acid is. Determine the functionality of adipic acid available for condensation reaction with the ethylene glycol. This is a similar question of what was discussed even in the course, where they asked about, if I'm not wrong, the functionality of an allyl alcohol um, for its reaction with, I think, some carboxylic based compound. Any answers? Two, yes, by functionality. So let's see the structure. Okay, so let me zoom in. So this is the adipic acid. I hope everybody now would have been aware, because we discussed about nylon 6,6. So over there we use adipic acid and hexamethylene diamine as our set of monomers to form this polymer. This is adipic acid and this is ethylene glycol. So the OH group from this ethylene glycol will basically combine with the hydrogen from the carbon atom, and then they will what do you say, gets condensed out as product, as condensation product, and then the polymer will be formed. So can anyone tell me why the functionality is 2 here? Because only one part of this COH group and OH group is reacting, but why it is made why people are saying it as 2? I hope my question is clear. So here only the COH group, one COH group and one OH group is reacting. So why is that the functionality of this adipic acid is going to be 2? Unable to see. Is it okay. Let me just hmm. So why is the functionality 2? I mean, I think that is very, hopefully, I think it's a very trivial question, because it has two carboxylic acid group, and this is only I'm representing it as a one particular repeating unit. The two monomers are reacting with each other, and then they form a one repeating unit which will is going to get repeated. So there will be some other ethylene glycol molecules also coming towards this side to react with adipic acid. So this carboxylic group that is present will react with that ethylene glycol. And similarly for ethylene glycol, so suppose if I ask the functionality of ethylene glycol with respect to adipic acid, then also it's going to be 2, because through this position another one adipic acid will come and come and react with this OH group of this ethylene glycol that you see. So there will be, so for either of them, either adipic acid or ethylene glycol, the number of functional groups or the functionality available for condensation reaction with respect to the other one in this case is going to be 2. However, that may not be always the case. So let's go on. So let's go to this numericals first. We have one question to discuss. We will discuss that. Let's me, yeah, yeah. Question number 6. It's a GATE 2018 question. The degree of polymerization of polymethyl methacrylate sample having a number average molecular weight of 1,50,000 gram per mole is. So what is the degree of polymerization of polymethyl methacrylate? PMMA. You need to calculate and oh, am I audible? Just a second. Let me try to switch my network. Let me stop sharing this. I hope now it is fine. So if you are finding it difficult to get that methyl methacrylate units molar mass, then you are always welcome to, if possible, you can check the structure in the internet if it is okay with you. Or I can give the empirical, I mean, without the structure, I can just give the molecular formula. Just a second. So this is the molecular formula of that repeating unit, methyl methacrylate. Somebody 1500 is the degree of polymerization somebody has mentioned. So let's see. Let us wait for few minutes, just 1 or 2 minutes for others to let's see whether they are able to solve the problem. Degree of polymerization. It basically represents what it signifies is how many times this repeating units are going to repeat itself. That's the only thing. So, so try solving the problem because these questions are very similar to what you will be getting in your assignments as well as again. So if you see this is a GATE 2018 question, so it will be very helpful if you are planning to appear for the GATE exam anytime sooner or later. Yes, anyone else answers? 1500. uh are you sure whether the I mean what you have written in the chat box, molar weight or molecular weight of monomer by molecular weight of polymer? Polymer by polymer, okay. So what is this mo- uh, molar mass of this repeating unit coming out as? Molar mass of repeating unit, what is this C5H8O2 is coming out as? Interesting. DP is 1786. Okay. So let's try to calculate. So I hope there is no confusion that methyl methacrylate is C5H8O2. You guys can always, if possible, you can Google it out and check. It. I should have had the structure with me. So apologies for that. So it should be 12 times 5 plus 8 times 1 plus 16 times 2. How much is this? 12 fives are 60 plus 8 plus 32, which is nothing but 100 gram per mole. 100. So degree of polymerization is nothing but we have to just get the number of repeating units in the polymer in the chain. So that is nothing but degree of polymerization is equal to number average molecular weight divided by the molar mass of repeating unit. So that is nothing but degree of polymerization is equal to 1,50,000 by 100. That is 1,500. So this is what I am getting as answer, but I guess one person, Trisha, you have got a degree of polymerization as 1786. Could you please, explain like how did you get that value? Yes. Okay. Okay. That's fine. So yeah. So this is a very simple example on how to calculate the degree of polymerization based on the number average molecular weight by molar mass of the repeating units. So if you divide both of them, so if you basically multiply the number of repeating units or basically the degree of polymerization with the molar mass of the repeating units, what you're actually going to get is nothing but is the number average molecular weight. Before that, let's go to this last question. We will come back to those two a little bit later, but let's do this. This will basically give more clarity on how to calculate number average molecular weight and then on weight average molecular weight as well as the polydispersity. So the question reads as something like this. So question number would be, I think it's a bit mismatched. 9. So if 5 gram of a monodisperse polystyrene sample of molecular weight 10,000 gram per mole is mixed with 15 gram of another monodisperse polystyrene sample of molecular weight 20,000, calculate the polydispersity of the resulting mixture. Take few minutes of time to think over it and then let us discuss this. And of course, if you get the answers, then you are always welcome to post it in the chat box. So, what is the meaning of the word monodisperse polystyrene sample? What do you mean by monodisperse? Polymer chains are based typically of similar length or similar size, you can say. It's better. It's better to say similar length. So, any answers for this question? I'll start solving within another 2 minutes, 1 or 2 minutes. Or anyone can at least like tell me how did you actually start solving the question. Of course, to calculate polydispersity, you need to calculate number average and weight average molecular weight, and then you need to divide both of them so that you can get polydispersity. And you know how to calculate weight average as well as number average. I believe everybody knows. So let me start. So I'm going to take this 5 gram of PS. PS is polystyrene. Sample sample 1 is this 5 gram of polystyrene with the molecular weight of 10,000 gram per mole. And I have another sample 2 which is 15 grams of PS with a molecular weight of 20,000 gram per mole. Or let's keep this as sample P and the sample Q. That would be much better. This is the first step. Now we are supposed to calculate the polydispersity index, or so here we have to calculate first the number average as well as that of the weight average. So polydispersity index, or you can just write it as dispersity also, is nothing but it is equal to weight average molecular weight divided by the number average molecular. So weight average is nothing but weight average, you can calculate it as Ni Mi square, just a second, divided by Ni Mi. Is this correct? So this is the weight average molecular weights formula. Now number average, it is going to be NiMi divided by Ni. Am I right, or is there any mistake with the way we have written? Here we have two samples, so every that summation will be having two components. So if you see for weight average, it would be NP times MP square plus NQ times MQ square, the whole divided by NP times MP plus NQ times MQ. Is this okay? Similarly, for number average, you write it as NP MP plus like NQ times MQ divided by NP plus MP. Sorry, NP plus NQ. Now, how do you calculate NP and NQ? MP and MQ is fine. MP is the molecular weight of that sample P, and MQ is the molecular weight of sample Q. So that are given. How to calculate NP and NQ? So can I what so what will be, how will I write NPS? which is 10,000. Okay. And the NQ will be similar, so that will be 15 by, sorry, 15 divided by 20,000. Is this fine? Okay. So I think now it is just mathematics. You need to tell me what is weight average and what is number average. It's better to calculate this in the form of fractions so that it would be more quick. I mean, you can finish solve it fast. Of course, without a calculator. If you are using a calculator, then it's fine. Anything. As far as my experience is concerned with this NPTEL exam, I think the virtual calculator will be used. It will be allowed. You can use a virtual calculator. So I will also use my calculator here with me. Uh, or is it possible? Alright, okay. And number average will be NP times MP. Oh, I hope this is the fraction that you will get. So I'll just use my calculator and then calculate this. So polydispersity index will be nothing but dispersity is 17,500 divided by 16,000. That would be 175 by 160. 1.09. So polydispersity index for this particular mixture is 1.09. Any other answers apart from this? I don't know. My calculations might have went wrong. Now, okay. Okay. Any questions or anything which is which you are not able to get, especially in the last three steps, because I directly wrote it with the value. So this polydispersity index as such is it will be greater than 1 or equal to 1. So as I said, it is, if it is equal to 1, then it will be very easy for processing, because almost all the polymer chains that you will be having within the system, or the bulk or the sample of the interest that you're taking, will be of the same size. So processing will be a bit easier, and anything greater than 1 is fine. But usually always it is a case that polydispersity index is not less than 1. So why is the question? And if any of you have answers today for that, then please let me know. Or this something, again, I'll put for, I am actually giving it to you as a question, or asking why is this polydispersity index cannot be less than 1. So PDI is polydispersity index, acronym for that. let me put this question. What about, yes. Hmm. Hmm. Okay. Hmm. 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 So, well, yeah, yeah. So let me just list down what does each of these represents, because sometimes there may be chances that that wi what they are representing over there, it's just that the notation might be different, but then the meaning might be the same. So I'm not sure which source you actually went through, but let me just list down here what each represents, so that it will be easy for everyone. So I basically represents for, this is there again in the course, so if you guys, you guys can also go and look at that. Oh, okay, so I basically represents for the number of repeating units. Ni basically represents for number of macromolecules with I repeating units. I will put this in the, yeah, 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 yeah. And mi, or okay, first let me write, is nothing but mass, not molar mass, mass of macromolecules with I repeating units. So this mi can be represented as ni, uh, just a second, I times m naught. So m naught is nothing but it is the molar mass of the repeating units. So MO is the molar mass of the repeating units. So that times the I will basically give the, what do you say, molar mass of the macromolecule with the I repeating units. That times the number of repeating units, or basically the number of moles that you say, will give you mass of the macromolecule with the I repeating units. So is there, I mean, is there still that contradiction? I mean, any okay, so I is basically the number of repeating units in a chain in the macromolecule. Ni is nothing but the number of macromolecules with the I repeating units. Mi is nothing but it is the mass, not molar mass, mass of the macromolecule with the I repeating units, and this Mi is represented as Ni times I times Mo. So this Mo is the molar mass of the repeating unit. If you multiply that with the number of repeating unit, you will be able to get the molar mass of the macromolecules with that I repeating unit. So that entire macromolecule, that molar mass. If you multiply that with the Ni, then you will get the mass of the macromolecule with the I repeating units. Yeah, yeah, yeah. Yes, yes, yes. Again, hmm. No, no, no. No. I is the number of repeating units. So if you take one whatever this macromolecule chain, the number of repeating units that is there in that macromolecule, that is I. So like that, so with the similar repeat, let's say 10 repeating units, like that 10 repeating units, you might have many different molecular chains in a bulk sample. Not like they are in an isolated system. So assume it is a bulk sample, and then you have multiple what do you say, molar multiple macromolecules. So there may be many macromolecules with a similar number of repeating units, right? So I is basically the number of repeating units, and Ni is basically how many macromolecules has this I repeating units. So let's say I take a system, bulk system, where there are, let's say, 100 macromolecule chain. So out of this 100 macromolecule chain, let's consider 10 of them have 20 repeating units in a structure. So repeating units basically determine the length, right? So 20 of them have 10 repeating units. So Ni is nothing but that 20. Is that fine? And this again, somebody told me whether this Ni times I times Mo can also be taken as Wi. Yes, that is true. But that Wi is the mass of the, again, it's just a alternate term, mass of the macromolecules. You can also represent this as Wi. I'm not going to make it the more confusion. But the summation of this NIMI, that is uh, mass of all the macromolecules in the sample with this I repeating units is going to be overall mass of the sample. I think it's going to be more confusing here because this number of repeating units, but then it's so as I said, in a bulk sample, when you take, it's not necessary that all the polymer chains will basically have the same number of repeating units, because the processing conditions might be different. So every time whenever you get, you might get different polymer chain with a different number of repeating units. That is the reason we do not define that is the reason for polymers we basically define a molecular weight distribution, because uh, depending upon the number of repeating units, the molecular weight will change. So that is the reason they have a distribution and not like uh, molecular weight like of a particular compound. How do we define, like let's say CH4 methane, it is 16. We do not define it like that. We put up a distribution, and then based on that distribution we define different types of molecular weights, like weight average molecular weight, number average molecular weight. So we will be having polymer chain or macromolecule chain with a different number of repeating units. We take, so I here represents for how many repeating units are there in that macromolecule chain. Ni represents how many macromolecules have that I repeating units. Let's say there is a bulk sample. Again, I'm going to take the same example. 100 macromolecule chain is there in a bulk sample. Each macromolecule chain has, let's say 10 macromolecule chain has 10 repeating units. So Ni will be that 10, and Mi is nothing but molar mass of that one repeating unit times the number of repeating units. So this will be nothing but, let me write that also, I times MO will be nothing but molar mass of the macromolecule. So this will be something like, let's say that M naught is 100, and if I have, let's say, 10 repeating units, so this will be 10 times that 1000. So this is for one macromolecule chain. Like that you have n number, right? So you need to multiply that n to get the mass of that macromolecule. So that is Mi. And like that, so this is for one particular what do you say, like for is 10. Like that I can also be 20, because we do not know how it is going to be come out. So for that I of 20 you have separate NIMI. So like that, if you sum it all of them, you get W T. Let me write that all. So this will be under summation sign. So under summation NIMI will be nothing but the overall mass of the sample. Or if you want, I can just quickly write it down. So I mean, is it fine, or any doubt is still there? So let's say bulk sample, it has 100 macromolecule chain I'm talking about. Out of this, 10 macromolecule chain will have 10 repeating units. uh, Another 10 will have another 10 chains will have, let's say, 20 repeating units. Let's say another 40 chains has 30 repeating units. So like this it will be like for the other. So this 10 repeating unit represents the I. This is I. And this 10 macromolecule chain for 10 chains, and let's keep this as 20, or let's keep this as 30. So let this keep this as 50, so that it will be easy. So this 10 chains, 30 chains, and 40 chains is the Ni value, and that 10 repeating units, 20 repeating units, and 50 repeating unit is going to be the I value. So when you have this I, it will have a certain molar mass. So that you have to multiply with the number of repeating unit, then only you will be able to get the molar mass of one chain. If you multiply that molar mass of one chain with this 10, likewise similarly we have 10 chains. So if you multiply that with 10, then you will be able to get the mass of the macromolecule, which has 10 repeating units. Similarly, you have to, like, let's say that another let's say that 20 repeating units are there, so that you have to multiply like that 50. So it will be 50 times that molar mass of that repeating unit times number of chains, 40. So if you do like this for every single combination, and if you're going to add all of them, what you're going to get is the overall mass of the sample or the system that you're taking under consideration. So it's fine, right? I mean, any confusion or anything for anybody? Because I thought we will take up two more problems. We have actually two more, but it's fine. Let us take this next week so that people can get more clarity on this parameters. And yeah. Derivation in the sense I'm not able to like weight fraction. Mm. 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 So let me just think about this. Can you write mass of the macromolecule with the I repeating units divided by the total mass of the macromolecular unit? Mass of the macromolecule with the I repeating units, that is going to be a NIMI divided by total weight of the macromolecule, that is summation NIMI. It will be like NIMI divided by integral, what do you say, summation NIMI. I'll have to think about how to represent this in the weight fraction ratio. Somebody asked me regarding this, let me just stop sharing. Regarding this petroleum based polymer, like polymers, we said that they usually come, the raw materials comes from the petrol products. So what happens is, in case of this petroleum, when you take out that crude oil that comes out from there, you can try to extract out this polymer, the raw material for the polymer. So some common examples are usually your polyethylene, and even acrylic acid was also, it is given in as a example for the polymer derived from petroleum products. PP, polypropylene, yes. Polyethylene, polypropylene, and polyacrylic acid also. Acrylic acid as such is also generated from there. So I hope that addresses. And if you have any queries, you can let me know. Or if you have any feedback also, then you can always share it with me right now before we conclude our session. Yeah. Hmm. No, their raw materials for this polymer is extracted from there. It's not directly the polymer that comes out. Something like that. Hmm. So, any feedbacks from your side? Anything that you would like to see in this course, or you're always welcome to share that. Hmm. Okay. You mean okay, 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 okay. Yeah, okay. So let me just inform that also. So in the course page where you access these lectures, if you see in the top section, you can see that there will be a Q&A section, I believe. That name is discussion group. Yes, discussion group. So if you go to that discussions, it will be redirected to a page where you can post your questions, and if not me, somebody else from this else who's a part of this course will address to your queries. Hmm. So it will I am exactly not sure, but hopefully within a week or two it should be cleared. So it depends on the course to course actually. Hmm. Yeah, 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 I can understand. That's what. So you better pose the question, and let us know. Let us see by next week whether it gets answered or not, or otherwise, then I'll see what can be done. Yeah, okay, okay, thank you. So let me just conclude the session for today. So thank you everyone for joining today's live interaction session. Next live interaction session will be on 3rd August, same time, 5 p.m. to 7 p.m. on Sunday afternoon. So I thank Professor Abhijit Deshpande sir for providing me this opportunity, as well as the NPTEL team, to meet you all in this Sunday afternoon and interact with you guys. So I hope the session was useful for you. And let's see next week. Till then, keep solving your assignments and posting your doubts in the discussion groups. Till then, fine. See you. Bye. Yeah. Mm. Mm. Yeah. Mm. Like you can actually contact this NPTEL office of SWAYAM, asking them to extend the deadline, because usually what they do is between this first and second week assignment the deadline would be approximately the same. It will be on mostly on the same date, or probably there will be a day or two gap, not beyond that. So you can post your this thing to the to the NPTEL office, and then like I can I'm not exactly sure apart from that what we can do. Oh, okay, yeah, yeah. Okay, yeah. So thank you everyone. Thank you for joining. Yeah, bye.